Hello everyone, I'm from Team 7. I'm Raditya Furitama and I'm about to present our project which is pneumonia detection from chest X-ray images. What is pneumonia? Pneumonia is an infection that inflames the air sacs in one or both lungs. The air sac might fill with fluid or pus, causing cough with phlegm or pus, fever, chills, and difficulty breathing. Pneumonia can range in seriousness from mild to life-threatening, and it is most serious for infants and young children, people older than age 65, and people with health problems or weakened immune systems. Each year, pneumonia affects about 450 million people globally. That's like 700 of the population, and results in about 4 million deaths. This project aims to diagnose whether someone has been infected with pneumonia based on the chest X-ray of the person. And we also want to classify whether the pneumonia is caused by bacteria or viruses based on the image. We believe that this kind of project will help thousands of people who are revealing that they are in symptoms of pneumonia, because this project can cause people to reduce their budget on seeing a doctor. People can also save their time from scheduling an appointment. They can straight get a timely treatment based on the classification that they got. Here are the objectives of our project. The first one is we want to analyze patients' chest X-ray images and identify whether the patient has pneumonia or not. And the second one we want to classify the type of pneumonia, whether the pneumonia is caused by bacteria or viruses. And here are some of the things that are being the challenges of our project. The first one is the imbalanced data set that may lead to biased data. The data set that we have is imbalanced, with the number of positive or pneumonia data having more samples than normal data. This may be a problem and may introduce bias in the classification. As CNN works best when training data is balanced, this problem may hinder the potential of the model that are proposed. We handle this problem by assigning class weight for each class. Detailed steps will be explained further. And the second one is there might be not enough data for creating a good model. The dataset contains a total of around 5,800 images. We know that models that are based on neural network is data hungry, meaning that they have to be fed many data so that we can get good results. A model that relies only on this data might not be enough to create a good classifier because of lack of data. And this problem might be affecting the overall performance of the model. Here are the related works that are already available and related to our project. Sarvai et al. Provide a technology approach and methodology for automatically and quickly classifying pneumonia. The author utilized two learning models, convolutional neural network and multilayer perceptron. Punit Gupta thinks that deep learning has the ability to achieve substantial characteristic in image classification tasks and to deliver medically better versions in image analysis. The author used the convolutional neural networks model and transfer learning principle. The last one. Rahman et al. Believe that a computer-aided diagnostic tool can significantly help the radiologist to take more clinically useful images and to identify pneumonia with its type immediately after acquisition. The author present a deep CNN-based transfer learning approach for the automatic detection of pneumonia and its classes. The author used AlexNet, ResNet, DenseNet, and SqueezeNet as the transfer learning of their models. The papers focused on how to diagnose pneumonia based on chest X-ray images and classify the pneumonia type of it. The papers cover issues that are similar for our proposed study, not only by technical means but also from methodology perspective. And all of these papers help us in getting the general idea of the project. and these related papers are our guidance for assembling the baseline models. Now we're moving on to data collecting. Um, we're now talking about data description. The data set contains images from chest X-ray that is focused on pneumonia diseases. We're using data that is provided from Kaggle. The data set was obtained from Manley data, and the original data set contains the chest X-ray data and optical coherence tomography. The chest X-ray images were selected from retrospective cohorts of pediatrics patients of 1 to 5 years old from Guangzhou Women and Children's Medical Center, Guangzhou. All chest X-ray imaging was performed as part of patients' routine clinical care, and the images pixels are around 1200 by 1000 pixels. We can see from the image, um, the left one is the example of normal X-ray with total of 1583 images. The center one is the chest X-ray with bacterial pneumonia with total of 2780 images, and the right one is the viral pneumonia with total of 1493 images. Now we're moving on to the image dimensions. We try to know what is the best shape that we can apply to the dataset in order to get the model to process the image as efficient as possible. We created a joint plot to see the sizes of the image that are found in the dataset. We can see of the left image, the dataset image dimension ranging from less than 500 pixel to more than 2000 pixel. The majority of image dimensions fell in about 1500 by 1000 pixels. But if we are using the shape, the model will be very heavy to compute and will consume many resources. So we will look at another way to determine the best shape to apply to the data. We then try to see the pixel intensity of an image to see the average pixel distribution in an image. We can see how the pixel varied in one size and get the final shape to apply to the data. We can see from the image on the right side, the pixel intensity mean is 156 with standard deviation of 47. We can also see in the plot that the highest pixel intensity is in range of 180 pixel. We can see that the high end of the plot is in 200 pixels, so we will try to use this shape to be applied to our data. Now we're moving to the data preprocessing part. We know that our data is in imbalanced state because of the bacterial class that is dominating in the data. We use class weight method to assign individual weight for each of the classes. This step helps us to gain non-biased weight towards the class that is the majority in the dataset. We get the weight by dividing the class count to the total of images. We can see that the weight for bacterial class is much higher than weight for the normal and viral class. Now we're talking about data augmentation. We use data augmentation in the image flow to see if we can classify image in different shape. We use image data generator from Keras. This step is crucial because this step can help the model to get the best weight out of an image. This step can also make sure that our model can handle any kind of image shape that will increase the robustness of our model. This step can clarify and enhance the image further because we can augment the data any way we want, from zooming to rotation. Keras image data generator can handle all of those tasks. as we can see in the left image, these are the parameters that we use for our project. We use validation split, which is the fraction of images reserved for validation, rescale, which is the rescaling factor, rotation range, which is the degree range for random rotations, width shift range, which is the fraction of total width, height shift range, which is fraction of total height, and shear range, which is the shear angle in counterclockwise direction in degrees, zoom range, which is the range of random zoom, sample-wise center, which is the set each sample mean to 0, and sample-wise standard normalization, which is the divide each input by its standard deviation. We can see in on the right side image, these are the result after preprocessing the data. Now we are moving to the methodology that we used. The first models that we use is convolutional neural network. It is a deep learning algorithm which can take in an input image, assign importance to various aspects or objects in the image and be able to differentiate one from the other. The preprocessing required in the ConvNet is much lower as compared to other classification algorithms. While in primitive methods, filters are hand-engineered. With enough training, convolutional neural networks have the ability to learn these filters or characteristics. And usually when there is a problem that involves image identification, convolutional neural networks is usually used and has become the standard solution to deal with the identification. Next, the second methodology that we use is transfer learning. We also using transfer learning technique as the approach to the identification. Transfer learning is a machine learning method where a model developed for a task is reused as the starting point for a model on a second task. By applying transfer learning to a new task, one can achieve significantly higher performance than training with only a small amount of data. Transfer learning is so common that it is rare to train a model for an image or natural language processing related tasks from scratch. Transfer learning has the benefit of decreasing the training time for a neural network model and can result in lower generalization error. And the transfer learning models that we use will be explained sooner. The first transfer learning models that we use is VGG16. VGG16 is a type of convolutional neural network that is considered to be one of the best computer vision models to date. The creators of VGG16 evaluated the networks and increased the depth using an architecture with very small convolution filters, which showed a significant improvement on the prior art configurations. They pushed the depth to 16 to 19 weight layers, making an approximate 138 trainable parameters. And the most unique thing about VG16 is that instead of having a large number of hyperparameter, they focused on having convolutional layers of 3x3 filter with a stride 1 and always use the same padding and max pool layer of 2x2 filters of stride 2. The second model that we use is ResNet. ResNet, short for residual network, is a specific type of neural network that was introduced in 2015. And mostly in order to solve a complex problem, ResNet stacks some additional layers in the deep neural networks, which results in improved accuracy and performance. The intuition behind adding more layers is that these layers progressively learn more complex features. For example, in case of recognizing images, the first The first layer may learn to detect edges, the second layer may learn to identify textures, and similarly, the third layer can learn to detect objects, and so on. Next, the model that we used is DenseNet. DenseNet is one of the new discoveries in neural networks for visual object recognition. DenseNet is quite like ResNet with some fundamental differences. ResNet uses an additive method that merges the previous layer with the future layer, whereas DenseNet concatenates the output of the previous layer with the future layer. DenseNet was developed specifically to improve the decline accuracy caused by the vanishing gradient in high-level neural networks. In simpler terms, due to the longer path between the input layer and the output layer, the information vanishes before reaching its destination. Next, the model that we use are Inception V3. Inception V3 is an image recognition model that has been shown to attain greater than 78.1% accuracy on the ImageNet dataset. The model is the culmination of many ideas developed by multiple researchers over the years. The model itself is made up of symmetric and asymmetric building blocks, including convolutional, average pooling, max pooling, concatenations, dropouts, and fully connected layers. Batch normalization is used extensively throughout the model and applied to activation inputs. And the loss is computed using softmax. Um, the last model that you use is exception. Exception is a deep convolutional neural network architecture that involves depthwise separable convolutions. Exception stands for extreme inception. It takes the principle of inception to an extreme. One of the differences between inception and exception is the presence of or absence of a nonlinearity after the first operation. In inception model, both operations are followed by a ReLU, nonlinearity. However, exception doesn't introduce any nonlinearity. Now we're moving on to the models. From the image on the left side, we can see this is the baseline CNN architecture of our models. Um, we can see that the total trainable parameters that are available is uh, is about 7 million. We can see that there are a total of 19 layers for the baseline model, which is the conv2d layer, which creates a convolution kernel that is convolved with the layer input to produce a tensor of outputs. And the next layer is max pooling 2D, which downsamples the input along its spatial dimensions by taking the maximum value over an input window for each channel of the input. Um, and the next layer that we use is flatten layer, which is basically um, flatten the layer to one dimensional shape. And we also use dropout layer, which randomly sets input units to zero with a frequency of rate at each step during training time, which helps prevent overfitting. This layer is kind of like the regularizer for the network. And the last layer that we use is dense layer, which is just a regular hidden densely connected layer. We can see that the input shape is the same as the image size that we get before, and for the output layer, three neurons are the are assigned for the total class that we want to predict. And here we can see the architecture of our transfer learning model. We can see that despite the total parameters is about 23 millions, the total trainable parameters are only 1 million. This is because we froze the best functional layer so that the functional layer cannot be trained in our model. And we extend the model by adding more hidden layer after getting the output from the pooling layer. We can see that there are a total of 15 layers for the transfer learning model. Um, we can see that we have the global average pooling duty and the batch normalization layer, with the layer which normalizes inputs. Batch normalization applies a transformation that maintains the mean output close to 0 and the output standard deviation close to 1. And the rest is kind of the same that than before. Now we're talking about the activation function that we use. The first activation function that we use is rectified linear unit, or RLU. It is a piecewise linear function that will output the input directly if it's positive. Otherwise, it will output 0. It has become the default activation function for many types of neural networks because a model that uses it is easier to train and often achieves better performance. Yeah, we use ReLU for all the hidden layers in the model. The next activation function that we use is softmax. The softmax function converts a vector of k real values into a vector of k real values that total to 1. The softmax translates input values that are positive, negative, 0, or higher than 1 into values between 0 and 1, letting them to be evaluated as probabilities. Now we're talking about the loss function and optimizers. The loss function that we use is categorical cross entropy. Categorical cross entropy is the default loss function to use for multi-class classification problems. It is common for categorical cross entropy to be used when dealing with multi-class problem. Thus, we apply this as our loss function. And the first optimizer that we use is Adam. Adam optimization algorithm is an extension to stochastic gradient descent that has recently seen broader adoption for deep learning applications in computer vision and natural language processing. Adam is an optimization algorithm that can be used instead of the classical stochastic gradient descent procedure to update network with iterative based in training data. Many believe that Adam is the best optimizer because Adam takes benefits from two optimizers, RMS-prop and AdaGrad. Yeah, because because Adam is considered the best, thus we use this optimizer for our models. The next optimizer that we use is RMS-prop. RMS-prop is an extension of gradient descent and the AdaGrad version of gradient descent that use a decaying average of partial gradients in the adoption of the step size for each parameter. The use of a decaying moving average allows the algorithm to forget early gradients and focus on the most recently observed partial gradients seen during the progress of the search, overcoming the limitation of AdaGrad. Yeah, we want to compare RMS-prop with Adam to see which of these two optimizers works best for our image data. And here are the training parameters of our models. We use 20 steps in epoch and batch size with total number of images, floor deficit by 64, And the validation data that we use is 20% split from training data, and the learning rate for optimizers is 0.0001. We also use early stopping. Early stopping literally means stop training when a monitored metric has stopped improving. We use this to prevent the model to have decreased performance, and we monitor it through validation accuracy with set patient with set patients of 3 epochs. We also set the restore best weights back if the latest weights are worse than the best value. And here is here's the result after we train our model. Um, we created a comparison table to see the performances for all the models in terms of precision, recall, F1, accuracy, um, ROCOs, AUC score, and training time. Um, we can see the results from various models that we have tested. We tested a total of 14 models in which they are differentiated from the optimizer that we use, which are ADAM and RMS Pro. Typically, we are interested to see the F1 and accuracy score when we want to evaluate classifier model. In terms of macro average F1 score, we can see that baseline CNN with non-augmented images and ADAM optimizer has the highest score among all models with 77%, and the VGG with RMS prop optimizer has the lowest score with 54%. We can conclude that in terms of balance between precision and recall, VGG RMS prop is the worst of all models. Next metric that we want to see is the accuracy score. Again, we can see that the baseline CNN with non-augmented images and ADAM optimizer has the best accuracy out of all models with 80% accuracy. And Inception with ADAM optimizer being the worst model with accuracy of 66%. We can conclude that based on the comparison table, it is better to use RMS prop for inception model rather than ADAM for the data that we use because the accuracy is higher by 7%. In terms of ROC AUC score, we can see similar result as we get from the F1 evaluation. We can see baseline CNN with non-augmented images and ADAM optimizer being the highest scoring model and VGG with RMS prop optimizer being the lowest scoring model. In terms of training time, you can see that using scaled non-augmented data gives us fastest training process by much. With only less than 2 minutes, our baseline CNN models when using non-augmented data can give us the best results among all models. And yeah, in terms of comparison between ADAM and RMS prop, we can see variations between the results. Sometimes ADAM yields better F1 and accuracy score. Sometimes RMS prop outshines ADAM. Sometimes they both give the same results. So we conclude that both optimizers perform the same for our data. Now we evaluate the model based of the accuracy and loss plot. We can see that the best model went through 15 epochs, and also we can see that from the accuracy evolution plot, even though the validation accuracy is the highest from all models, we can see that the accuracy stopped evolving after 12 epoch and tended to go down afterward. The highest jump happened in the second epoch. We can see that the training and the validation accuracies are both aligned nicely, meaning that the biases from training data influence the validation data. And as from the worst model went through only 4 epochs. That explains why the model performed poorly. It didn't get to have the adequate training time, and we can see that there's a major accuracy drop from the second epoch. And the third and fourth epoch couldn't reach the previous best accuracy. That's why the early stopping cut the training process prematurely. We can see that the accuracy lines al- don't don't align with each other, meaning that the biases are not enough to influence the validation data. Now we now we can see from the classification report. Um, we can see various of metrics from the best models. We can see that the recall for bacterial and normal classes are both good by above 90%, but when it comes to viral class, the recall dropped drastically from the other two classes. We can see that the precision from normal class is way higher than both pneumonia classes, meaning that the model can classify normal images pretty good, but when classifying both of pneumonia classes, the model still struggles to differentiate them. The performance is also reflected on the F1 score. We can see that for normal class, the model did a good job with 91% score and did a poor performance when classifying both pneumonia classes. And and we can see from the classification report from the worst model, the pattern of scores is quite different from the best model. All of the scores for viral class are 0%, meaning that the model couldn't classify viral class even for just one image. The normal class scores are reduced by 5%, and it seems that the model can classify bacterial class better than the best model because the recall score is 99%. Now we look to the ROC plot of our best and worst model. We can see from the best model, the normal class curve is almost reaching the edge with score of 0.94, meaning that our best model can classify normal class images with a great performance. And for the pneumonia classes, which are bacterial and viral, we can see that the curve is more leaning to the middle and the scores are both 0.82 and 0.71 with bacterial class above viral class. This means that our best model still struggles to differentiate between bacterial and viral images, with viral class being the harder one to classify. Now we look to the worst model ROC plot. Um, we can see that when it comes to the normal class, the model still can differentiate it pretty well, even though it's not as good as the best model, which with a score of 0.90%, 0.90. The curve also tends to lie towards the edge. However, we can see from our pneumonia classes, both classes don't perform well enough. You can see that the line for viral class goes perfect straight with score of point, 0.50, meaning that our worst model couldn't even classify viral images even for just one image. And now for the last comparison that we want to see is from the confusion metrics. We can see that from the confusion metrics for the best model, we can see that it is still pretty difficult for the model to classify the viral images. And we can see that the model mistook viral class for bacterial class by 133 images. Um, this number is pretty high compared to other errors that are less than 50 images. We can also see that the errors for normal class are the lowest from all errors. Um, Now we're moving on to the confusion metrics for the worst model. We can see that the model performed poorly. We can see that the model can't even classify the viral image in the test data. The model got 0 in predicting viral images and mistook all of it for bacterial class. There's also nothing that the model predicted for viral class. The result of normal class is slightly reduced in the worst model. We can conclude For this first model, the model's bias for viral class didn't influence the model enough. Now we're moving on to the conclusion or outcomes or finding. The first one is based on the models that we have tested, the baseline CNN models without data augmentation are the best performing with the fastest training time. Um, this Next, we got variation of results between Adam and Adam's prop, so we can say which one is better for from these two optimizers. And then we can see that for all models that we have tested, the models struggle to differentiate between bacterial and viral class. Um, Next, the VGG with RMS prop optimizer is the model that yield worse results. But we conclude that because the training process was cut prematurely by the early stopping mechanism. And even though the models struggle to classify between two pneumonia classes, the models can classify normal class pretty well. We conclude that if we make this project a binary problem between normal and pneumonia only, the accuracies for all models will be much better. Um, and last thing is, all of the models were trained by short epochs and early stopping. Um, if the epochs were longer and early stopping mechanism was set longer in patients, it may be resulting in better performing models. And here are the things that we consider to be the feature improvement for our project. The first one is um, we are planning to increase the accuracy for prediction between bacterial and viral. We will try to make the models classify between these two pneumonia classes better. The next one is we are planning to apply cross validation. Um, yeah, we didn't apply any validation for any of the model. There's all there was also no hyperparameter tuning performed in all of our model. We think that by applying cross validation, we can increase the accuracies for our models greatly. And the last thing that we want to do is to add more disease classes based on the chest X-ray images. For example, like COVID and tuberculosis data. We believe that by accomplishing these tasks, we are able to significantly improve our project. So that's all from our project. Thank you for listening. Thank you.